Thank you. Thank you for the presentation, Julia, and a little bit what we wanted to tell you in this presentation of the applications and products. What applications and what products we could develop around the radar technology, not only for the SAOCOM mission that we are developing now, but the SAOCOM mission. From the SAOCOM mission, we have also developed some products using not only the first satellite that was in orbit in the L-band, which was from the Japanese space agency, but also from the Italian agency, and this constellation that Engineer Perez has already mentioned about the Italian and Argentinian system or cooperation. One of the things that I wanted to mention first, I wanted to see first, is why we use radar technology, what this is good for. So Josefina told you about we created our own electromagnetic wave so we can create images during the day and night. We don't depend on the solar light or the sunlight, so we can have images, take images in every type of weather. We can cross the cloud coverage. Yes, so we have a reading of 24 centimeters of 1.75 gigahertz, 1.275 gigahertz. One of the main characteristics of this technology was the measurement of the distance, which allows us to apply applications with different telemetry. Other characteristics of this radar technology is that it gives us an idea of the structural properties, as well as the optical images give us an idea of the distance of the targets, how the light is reflected. What we can observe with the radar technology is how those structures are, how the electromagnetic wave interacts with those targets, and that will allow us developing some applications around that. The other characteristic is that we have the capacity not only to penetrate to the locations, but we can also within the soil, and that will allow us estimating moisture of the first centimeters of the ground. For this type of technology, and the ground may be sandy, and the wave length may enter into the ground 2 meters. For soils that we work with, agricultural soils where we want to check on moisture or the deserted areas, so we assume that approximately we can enter into the around 5 to 10 centimeters of the ground. So we may extract the reading of moisture. And the main characteristic, as Josefina stated, one of the objectives of the mission was to create a satellite sensitive to electric properties, to the dielectric properties. So the SAOCOM is unique because it was built around one of the main objectives and the moisture of the soil. Then I can tell you about these maps that we are generating of SAOCOM, but having applied engineering as one of the requirements, one of the first questions was, you want to moisture the you want to measure the moisture of the soil, but what are your requirements? What are the ambiguities? Which is the error that the calibration constants have to have? How do they have to be the sensors? How should the sensors be? For all of those questions from the scientific side, it took us to a year and a half of work with the collaboration with INBAF, so to us to answer those questions and to be able, and with those answers that we gave to the questions, to change and to give a new shape to the design that was creating of the antenna, as Josefina stated. So we needed certain requirements and certain characteristics, and having requested that for the antenna, it makes it a unique antenna due to its sensitivity to measure moisture. So it's a unique antenna in the world. So before we start with the applications, I wanted to tell you about the modes of acquisition for SAOCOM. We have the strip map with the coverage less than 10 kilometers, less than 10 meters on a single point. Then we have the tops are narrow. The tops are mode. It's the first time implemented in an asynthetic radar. The tops are mode. The first satellite was the Sentinel from the European satellites. Then the second one, the SAOCOM, to implement this type of acquisitions. And we have the tops are narrow and the tops are wide. The tops are narrow. It is narrower of just 150 kilometers and with this, space resolutions of 30 meters. And then we have the tops are wide with a coverage of 350 kilometers. Yes, from 220 kilometers to 350 kilometers. And also with, yes, dual port. And the important thing about SAOCOM is that it's already providing images. The radar images, what they do is to send a polarized wave. What does that mean? So the electromagnetic field is vibrated, and that direction may be parallel to the ground. So there will be a rebound of the signal, and then it may get back to the satellite parallel to the ground, which is called a horizontal mode, or it may be perpendicular to the ground, and the electric field is called vertical. So we can get these components, the HHHV, HVV. First we, yes, send them in a horizontal way, then we get it vertically, or vice versa, and we can generate the different modes of organization. So SAOCOM has the characteristic to be able to send a circular signal and to be able to project to each of the components. And we may send circular waves, polarized, uh, go, going around like a clockwise way or counterclockwise. And then we may project one of each of the components. This is an experimental mode, a scientific mode to see what type of applications we may use. So in order to continue, let me explain, let me show you some of the applications we have developed with sensors. First, let me start with the interferometric applications. Since the radar has the capacity to measure with very good precision on the distance, we can create models with digital elevation. We can have the slopes and curves of the level, movement of structures, analysis of deformations, movements and deformations of the ground, a study of basins, subsidence of the soils, slopes again, and risk of volcanic eruptions. And we can also read the ashes and the lava deposits. All of these by using the interferometric readings with a differential reading with INSAR, and all of these applications that were developed around these characteristics, some, not all of them, but some, and I will try to show you how we have developed some of these applications. In this case in particular, it is something we did with the SpaceTech, the Japanese satellite, when the Kangoo volcano erupted in Chile, and the ashes reached also other areas. So we studied the movement with the differential, with the L-band characteristics and the SAOCOM. Not only we saw the movement of the ground, but also where those ashes were being deposited, and that also allows us to study and the mapping of the winds and to see if those ashes were going to reach Argentina or not, and how they were moving. And we applied interferometric studies, studying the differences of the phases and the coherence of the interferometric of the images and the temporal study of the images. The application, one of the most well-known applications, is to establish ground elevation models. Here we observe a digital reading with the SAOCOM in the province of San Juan in Argentina. And in this photo, we can observe the combination of the digital elevation and a calculation of the curves and the interferometric reading that gave us this digital elevation map of the zone. Other applications that we have where we have applied the SAOCOM photos are for studies of the movement of the glaciers using temporal images and observing how the differences in the phases and to observe how is the movement of the different components of the glaciers. This is an example by using SAOCOM images where we study the speed of the displacement. This is in the glacier Perito Moreno. What you see in red is the highest speed of movement from what's in blue. As you can see, the blue are next to precisely due to the erosion, the observation from the geosat, and it gives us an idea of highest or speed or highest speed of the from the glacier. Other applications that we have studied, but we have done this with satellites from the Italian Space Agency with the X band, in other words, with a band of around 3 centimeters. We have studied the coverage of the ground. In this case, particularly the area of Buenos Aires, the federal capital of Argentina, where we studied, is how there was the joining of the line of the subway in Argentina, how to the grounds when they started drilling and excavating on one avenue where the subway was working. So we studied how that sinkage was. So these applications have the potential not only to see the census of the soils of the grounds or the infrastructure works, but also they may be used, these ground elements, to study the water distribution or extraction of oil or mining exploitation or studies of heavy traffic. In other words, this analysis of subsidence gives us an idea of how many millimeters approximately have sinked or it is sinking, and we can use this for the different applications in this type of analysis. The red dots are those that are close to the radar, and the blue ones are away from the radar. So that gives us an idea of the movement or sinking. Another thing that using similar techniques in the scale readings, also this natural movement of the buildings. These are buildings in Puerto Madero in the capital as well, in Buenos Aires, using images from the Italian Space Agency Cosmo readings, how we observed these buildings, how they were moving some millimeters. Is the natural movement of the buildings and how they were moving some millimeters in a year, vertically as well as horizontally. So all of this leads us to be able to use this type of technology with these type of tools on movement formations. We can also use this for bridges. It has a huge potential to be able to perform good measurement. So whenever we perform an accurate measurement, we are saying that the satellites are at 600 kilometers and we're performing a specific measurements of movement and distance. So what is good is this type of technology. Also, we have used it for when we needed temporal analysis compared to photos, and we have used this from the Japanese satellite. We have studied the changes, how it was the urban expansion from the La Plata, and how the urban tracing has changed. And not only that, but it generates some masks, urban masks, precisely that allowing us to identify the changes in this urban setting, particularly in La Plata city. And another application we use the phase differences to study is to be able to establish the equivalent of water and snow. This is an application, a very useful one, because this photo in particular in the province of Mendoza in the valley of Tucungato is to be able to learn the availability of water that feeds the river that goes down the valley. It gives us an idea of the availability of water for the cultivations that are downwards, not down the valley. In some cases, for grapes or other cultivations. But it's to be able to establish the amount of water available by using satellite images, radar images particularly. And with this, we can establish, due to its sensitivity that the radars have for the change of permissivity of the soils, and we can translate that. So now let me tell you about some oceanographic applications, and I will show you the port. One of the ports here, I'm showing you the port of Callao in Lima. This is a photo in our catalog. It's a SAOCOM image, how you can see the boats at the port. But the oceanographic applications we aim at uh, checking on a spill of hydrocarbons. Not all of the dark spots we observe are for hydrocarbon or oil spills. It could be the contamination or pollution from the boats, determination of ocean winds, detection of vessels, detection and follow-up of icebergs, and navigation. This is in our catalog actually, and I wanted to show you, and I will show you how the application is. So what we do is to establish for this type of applications the spectral prints and to be able to estimate not only the geographical position of the vessels, but also to estimate which is the its length and its width, and to identify somehow that type of vessel, what type of vessel we're talking about. And in this case in particular, here there is a detection of a spill of oil or hydrocarbons. It looks dark, and how we can identify a dark spot due to the change of the clouds. The radars are also sensitive to the clouds over the oceans. So the less clouds, the image will be darker, and it will show these dark spots that we can imagine these are oil spills or hydrocarbons or other features. Precisely, we can detect them due to its change of the cloud coverage. So concerning the applications, this is a SAOCOM application on the platform, the ocean platform, where what we do is we determine the vessels there, It generates a report of all of the vessels we have on the ocean platform or fishing. Some vessels may be in legal fishing, others in illegal fishing. These reports can be given to the Navy, the naval in Argentina, to work in the early detection of these type of characteristics. Yes, of fishing vessels in the Argentinian Ocean. This is a SAOCOM image on Argentina. And these are all of the vessels that were detected in this region particularly. Other things that we can study is due to this sensitivity or the electric is that the changes in the saltiness. Particularly, I'm showing you a photo of the outcome of the Plata River coming into the ocean, and right in this area particularly, so that you may observe this, which is darker, and we will observe it as an image, which is the more diluted water and has a less response to desertification. This is the clean water that together that links the ocean, and here is the water with high response, showing that is more salty. And in this border between the river water and the ocean water, there is like a peak between in this change of salinity between or what we observe in this image. So very characteristic of these images when two water fronts join with different characteristics of saltiness. And other things also that we can observe here, we are in the platform of the Argentinian Ocean, and we can observe some wind twirls, like a cyclonic twirls. And if these are cyclonic, so what is showing us is that there is a rise of water from the depth to more superficial ones. And if they were anticyclonic, there would be a decrease. In this case, these are cyclonic. And that they are cyclonic, what is showing is an increase of nutrients of deeper waters to superficial waters. But if there is an increase of nutrients of these waters, what we can expect is to have, yes, fish. And what we're going to observe is here the vessels, the boats working in this area. Yes, because there's a presence of fish. There's a higher concentration of fish, of fish schools. Yes. Another characteristic that we can observe precisely is the cloudiness in above on top of the ocean, the changes of the clouds in the ocean. We can also identify the ocean winds. This is in Tierra del Fuego in the south, all the way to the south of Argentina, where we to be able to determine how the waves determine, and this change in the photo allows us to determine the influence of the wind, and it can be used for the navigation in the ocean. Something else where we have used SAOCOM images or photos. Last year in the Antarctic campaign, our boat, the Icon boat, SAOCOM images were used, and also from Italian images, precisely to show to the boat how to navigate in those areas, because they needed to determine how to arrive from here on this point. We see they had to go to the south to the Marambio base, but it had to go through a very important accumulation of ice, and it had to save fuel. So it had to see how to be able to navigate in those waters. And in general, in this type of places, There is also, of course, weather adversity, lots of clouds. So radar images are used that were sent to the boat precisely to indicate how the distribution of the ice was there, the continental ice, yes, and so to communicate this to the boat to be able to reach the base. Well, and now I will tell you about some agricultural applications and environmental applications. This is in Majes in Arequipa in Peru. I wanted to show you how a SAOCOM image is on agricultural lands. They are darker, and we may think of places that are not cultivated, and what is greener are, yes, areas that are cultivated, agricultural areas. I wanted to show you a SACO image for this type of applications, also for the monitoring of water bodies, the study of floods, classification environments and vegetation, identification of productive areas, content of water in the plants, the rate of radar vegetation, sensitivity to rugosity, moisture of the soil, the index or rate of droughts, deforestation, and determination of fires. This is a SAOCOM image from Belleville in Cordoba. This is the area of Belleville. It is polymetric image. We use Pauli. It is a polymetric combination of the HH waves, HVA, precisely to classify in these environments and to be able to determine, for instance, here I took this a cut of the region to be able to determine the pink area are the highest vegetation. These images in simultaneously with campaigns of fields in the region. That's why we observe these that I'm showing you are photos that were taken simultaneously with SAOCOM, and these cultivations that are in the pink areas, they are, yes, higher. And the colors greener, we can relate them to lower cultivation, and they have a, yes, a response, better response to the image radar image. So this is called like a rebound with those characteristics. And the darker areas, we associate them with the naked areas or with uh, water bodies. And then we perform an analysis of the cloudiness. Here we can assert also the rugosity. After the machine went over the area, it allows us to see how the land is, how the ground is, how is the rugosity. So the since the satellite is so sensitive, it allows us not only observing the direction of the seeding, but also how the land was left after the passing of the machine. This is an example we had with Sentinel images that we worked together with the National Institute of Agricultural Office from Buenos Aires and the Institute of dedicated to agricultural applications. And one of the issues I had was to identify, for instance, in the region, which were potatoes and which were not. What you see in yellow here are cultivations of potatoes, and we did this by using Sentinel images because SAOCOM was not available yet, but we did it with temporal observation using European satellite images and how we could identify precisely the cultivations of potatoes in these fields as another application of the follow-up of cultivations that we can use that technology, this technology. And if we talk about the follow-up of cultivations, the technology we use these sensors with the rates of yes, rate of radar vegetation. So what we are sensing here is the structure of the cultivation and not a reflection or reflectance. When this structure grows, this rate or index is more intense, so we can perform a follow-up of the cultivation. And I wanted to show you, for instance, in this, if you see this region, around February the 2nd and February 18th, there was an expansion, a growth of the cultivation in this region is called Bendermill in the area of Cordoba. So we observed how the vegetation had grown, had expanded in this region. And by using this rate as well, normalized, what we have done, there have been many fires in Argentina in different areas of the country, but in this case in particular, we have used this rate in Entre Rios precisely to detect this change of vegetation, how you see the vegetation before and after the fire. Yes, and that by using a normalized rate beginning from the rate of vegetation, and it allowed us to verify where the fires took place. And you can see something in particular. What you observe in black is the comparison that we made between what we detected and the optical satellite, what we obtained from the optical satellite, the Landsat, by using a processing algorithm where we also determine the burnt areas with the optical images, and you can see that they match the optical images and the radar difference. This is a radar image in green, localized, but not only we detected the areas with optical images, but also observed some other areas that the optical did not see and did not see because in this area, if you get an optical image, there was some smoke on this area and the optical image could not go through the smoke. But we also detected this this image that the optical image could not take. But one of the important things that the satellite can do then, it is the sensitivity to the water, not only the free water, but also the groundwater. And I wanted to show you two images, one from the Amazon, how the Amazon is observed in one of the regions of Peru, how we can observe the Titicaca Lake between Peru and Bolivia. These are SAOCOM images, and they are in the catalog. And now I can show you what we do precisely. When we took these images here, I can show you this particular case in Argentina. And we also perform the detection of water, surface waters. So we can do a follow-up of the rivers, the ocean masks, where we observe the direction of the river, not only for the rivers, but also in areas where there could be some water deposits and there maybe was not contemplated in the original maps. So we can precisely the sensitivity we have to moisture, we can determine how the water bodies. But on the capacity to provide images for all type of climate, yes, going through the clouds and the penetration into the forestry and for the detection of water bodies. So we developed an application. One of the issues a company, a rice company had in Argentina, in the area of Corrientes in Argentina. So for them, in order to cultivate one of the characteristics is that they need to inundate the field with 5 to 10 millimeters in a uniform way. If it's not uniform, the rice won't grow evenly. So we performed a study with SAOCOM images and radar images. In the first date with optical images, we were able to detect which was where the water was distributed, the water was, and later where it was going through with SAOCOM, and we detected the regions with water. And when we went to the next Yes, time it was covered by clouds. We couldn't see with optical images, but we could capture them with the radar images, with the SAOCOM images. And then in a later day, there was like the rice crop was there, so the satellite could not penetrate to see that. So we, by changing the incidence, we were able to detect how the cultivation was being penetrated, and we observed the distribution of water, how uniform it was in the fields, corresponding to the surface water that they should have crossing the fields. In the fourth time, it was covered by clouds, but we were able to detect the covering of water on this region. So you can see from the characteristics of providing images and to go through the clouds, the capacity of penetration of vegetation and the sensitivity, that the electricity, we were able to develop this application for rice fields. And beside that, with radar images, it can determine, yeah, the rice per square meter and then have a follow-up cultivation and other characteristics that you can get with the radar. But I wanted to show you this because this is a particular three of the two aspects of the radar. We could apply them here in these fields. And as I have already mentioned, this sensitivity not only to the surface moisture, but also in the structures. What you can see here is an application that we developed with SAOCOM, starting from electromagnetic fields that we have in the plant that allows us to be able to determine the content of water at the plant, in the plant. So it's called the vegetation water content, the VWC. Also in this same area in the province of Cordoba in Argentina, and we can see the change of moisture of the plants from one day to another. Yes. So not only we want to have a census of surface waters or groundwaters, but we can also, with this type of sensors, we can observe the plant, the water in the plants. And here I can show you one of the first ground moisture maps that where this strip map. These are unique, these type of maps of the of moisture reading due to the capacity of the satellites. We can see for 180 to 500 meters, depending on the satellite we use. So when you use the strip map, are of low resolution. If we use the top sat, they are high resolution. But the good thing is of these maps is that this is a map in a strip map of high low resolution. And so if we focus in one lot, we can observe the changes in the moisture within the lot. And this may allow a farmer to determine if he has to water or not water, for instance, in the region. But why are we using the ground moisture satellites in SAOCOM? Precisely to establish the drought seasons. CONAE participates in the monitoring of droughts in the Republic of Argentina by providing maps of the moisture soils for the moisture in the soils in the whole country, and to be able to establish, together with other data that are contributed by other agencies, to be able to establish the distribution of the monitoring and the distribution of droughts around Argentina. Something else that we are using for the moisture is for weather forecasting. In 2014, the ground moisture was considered as an essential data precisely because by estimating the ground moisture improves the harvesting. Particularly, we are working with Meteorological Institute of Argentina in the face of science, precisely with different types of models that help precisely in assimilating moisture maps, and that they can help in this better in the diagnosis and forecasting. Also good for the cultivations. Very good to see how they grow. To also, of course, have a map of flooding or warning of floods from the in the with the ground moisture maps. So we have three strategic applications. One of those applications is a system of support of decisions in farming, in agriculture, that provides the farmer the possibility to upload the data from his field and to estimate. So we may see the estimation of how the forecasting is, and then I will show you the output of that application. And the other is to study, although we also study, is that the moisture, ground moisture or soil moisture we could use to establish the fusarium, where we could uh, link the ground moisture and how the fungus was distributed in the plants. In the past, this was established due to weather conditions, but the person who created the fusario in Argentina was how to observe the ground moisture may contribute to this type of models, and how to see how we could somehow give a warning of how this fungus could grow in the cultivation. And something else, another application we have used for is in the flooding warning. In other words, we assimilate the maps from the ground moisture in Argentina. So we establish with those models is how the flows of the rivers change in the basins, and we can establish a warning of the growth or the expansion of these rivers, and these warnings are reported automatically weekly to the Water Institute in Argentina, and it takes that information and it establishes how it is for these type of basins, how it is the growth of the rivers. And for also we have used the map is the propagation of plagues and disease by using the right environments. For instance, we have used for the plague of this expansion of the soil for the study of the environments, where there could be a propagation of these type of insects in the country given the conditions. So for the growth of the eggs of we're talking about the locusts, yes, the locusts or hoppers. Here I can show you another expansion of growth due to the rains around February 18th. Yes, from February the 2nd to February the 18th, you can see this expansion regionally. And these are the three applications I was telling you about of how the ground moisture maps helped as an input to generate agricultural support. As you can, if you visit the CONAE website, you are not going to find the catalog, the ground moisture readings, but also from SAOCOM developed maps depth for with the ESR readings and some COM and other sources for the depth of the soil. So what we give is a profile of the water body at around 50 centimeters. Now it may be different to complete the profile at different depths, but so far in the CONAE catalog you will find these maps of surface water, and with the average of moisture, yes, of 50 centimeters. That's what we have. Besides other additionally to other maps that are being developed, and this issue of the variation of the change of the scenarios for yes, the interannual variation of the medium of the different scenarios for the forecasting of the corn, how the irrigation forecasting was changed, and this is depending on the different type of cultivations. So we can establish scenarios and then compare them with the statistics precisely to have reliable yes data or information. This is what I was telling you about the fusarium, how this could be used in the region, and as I was telling you about the river density. This is an application that we have done. We needed a temporary evolution, but as you have observed, also to monitor the deforestation, but also used images from the Japanese space agency, Alos Pulsar and Jack from JAXA, and we could also use a temporary evolution from around 2008 to 2017 on how the deforestation was in this region in particular. Something else, due to the sensitivity and the dielectric importance, to be able to establish the covering for wet snow and areas of other types of zones, but yes, wetlands. This is also what we studied before, the comparison of wet areas, snow and water. The idea is to have the SAOCOM images and to apply the same methodologies for the SAOCOM images. And finally, Josefina has already told you about this emergency management and a particular product that is under development. Soon we will have it automatically. This is a unique product in the world because precisely we are providing the capacity to have 4 Italian satellites and 2 SAOCOM satellites to be able to generate products that will combine the benefits of both satellites. And I wanted to show you an example. This is how it is observed, the area of Posadas. This is a Paraná River in Misiones, how we can observe an image in the X band of the region. You can see here the details are very good. This is the space agency from the Italian agency. We have captured the afterwards of the same area with SAOCOM images, and you can observe different type of characteristics on the image. Here, maybe certain things were not detailed, but yes, there is a sensitivity that the X-band image did not detect, for instance, in the changes in the river and how the cities are observed and how the cultivated areas are observed. But if we combine those pieces of information, what we obtain is this type of products. This is a merge X plus L, and here what we combine, you can see that we can observe the cloudiness, the nubosity in the cloudiness that we saw in the X band, and you can see with the X band we could improve the characteristics of this image, of this photo. This type of merge is used in methodologies for merging. We wanted to show you that by combining both images, we generate a product that may help with for lots of applications, hyperspectral ones. And you can see these areas that are in light blue, they are naked soils, and the areas that look more highlighted like in 3D, they are areas with cultivations. So the benefits of the X band and the benefits of the L band that penetrate into the cultivations allow us to regulate these environments and characteristics that maybe with one image or the other we could not differentiate. But when we combine both, they are totally highlighted. These dots that you observe here, these dots, this is like electric line, a power line. You can see the bridges and also the tracing of the cities combining both images. And finally, we invite you to visit our CONAE website you can see our geo portal. You will find our SAOCOM catalog that Josefina showed you, and the general catalog that CONAE has, so that you may work with radar images. And here also this user page, and if you have any question directly, you can write your questions here. So thank you so much.